Hello, students. Very good afternoon. My name is Ravi Ranjan Kumar, and I welcome you all to this session. Okay, this week we are going to cover rotational motion, and it would be spread over 6 lectures. So, without losing any time, let's share our plan that what exactly we would be doing in these 6 lectures this week. Okay, so let me share my screen with you. So here it is. So what I have planned for you people in today's lecture, we are going to discuss first of all kinematics of fixed axis rotation, and then we will look into constraint relationship of rigid body, and then we will also try to cover moment of inertia, which is a very important physical parameter in order to discuss this behavior of rotation. Okay, and tomorrow's lecture, that is lecture number 2, we will discuss about torque, and then we will discuss about equilibrium of rigid bodies, and with that we'll take a few problems of toppling as well. Okay, and then we will discuss the concepts of angular momentum as well tomorrow. Okay, in third lecture we will talk about the dynamics of fixed axis rotation, and we will look into the famous equation tau is equal to I alpha and its application, and we will cover principle of conservation of angular momentum and principle of conservation of energy as well in third lecture. Okay, in lecture number 4 we will talk about combined translational and rotational motion. Then we will look into velocity, acceleration of any point on the rigid body in combined translational and rotational motion. And then we would be looking at the concept of instantaneous center of rotation. Okay, we will be discussing about this concept in detail in lecture number 4. Okay, and in lecture number 5, I plan to do the pure rolling. Okay, and apart from pure rolling, we will discuss forward and backward slipping in case of rolling, and we will also discuss about accelerated rolling. Okay, so lecture number 5 would be devoted to different types of rolling here. Okay, and the lecture 6 would be concluding one, and in that we will discuss the application of conservation of energy and conservation of angular momentum in combined translational and rotational motion. And we will be using impulse momentum theorems, angular impulse and linear impulse momentum theorem in combined translational and rotational motion. And lastly, we will look into multiple axis rotation. Okay, so this will uh, ensure that we cover, okay, the whole of rotational motion in the given week. Okay, and now let's come to the topic of today's lecture. So today's lecture we are going to discuss first of all kinematics of fixed axis rotation, and after that we'll be discussing constraint relations of rigid bodies, and lastly we will discuss moment of inertia. So let's begin. Okay, so here um, kinematics of fixed axis rotation. So let's start. So let's say we have a rigid body, okay, which is moving about a fixed axis. Let's say this is some x and this is x dash. Okay, so this rigid body is moving about fixed axis x dash with some instantaneous angular velocity omega. Okay, so obviously the direction of omega is this. This is the direction of omega over here. And let's say some O we take on the axis as origin. Okay. So now if we take any point on the rigid body, okay, so as this rigid body will rotate, this point here will undergo a circular motion. It will move along a circular path, we can say. And the center of this circular path would be somewhere over here. So say this here is the initial position vector Ri of this point. So as this rigid body moves about this axis, this point will move from somewhere from here to here. So this radius vector, this position vector over here, Rf, will become like this. Okay. So you must realize that the magnitude of Ri and Rf are same, only the direction has changed. Okay. And let's say this position vector makes an angle phi with the axis. Okay. So the point has moved from here to here on circular path. Okay. So its angular displacement, if we measure, okay, this angular displacement, okay, would be this term over here. So this we can write it as some d theta. So we are trying to find out the change in position vector, which would be dr vector, this vector over here. So this dr vector, first of all, let's try to find out the magnitude of this dr vector. And now looking in this triangle, let's name these points as C, and let's say this point is A and this point is B. So this, you see, ABC is an isosceles triangle over here. So dr, definitely we can write it as, if AC or AB, we term it as equal to R. So that would be simply R d theta. Okay. And R here, now looking in this triangle OAC, OAC would be a right angle triangle as well. So capital R, let's say the magnitude of this is R. So capital R would be nothing but R sine phi into d theta. Okay, so this is the magnitude of vector dr. Okay, and if we wish to write it is in vector form, we can write it as d theta cross r, because the magnitude of it would be r sine phi into d theta, or r d theta into sine phi over here. So this is it in vector form. Let's look at its direction also. So here you can say that d theta is directed towards uh, the angular displacement is directed towards in this direction. This is the direction of d theta. So d theta is upward. Okay. And position vector, for example, let's say is in this direction. So using right hand rule over here, so r d theta, we can simply say r d theta here would be along the direction of or d theta cross r here would be in inward direction. So that would be d theta cross r, that would be in inward direction. So we are able to look at this direction over here. So dr is basically along the tangential direction, and d theta is along the x dash axis, and this r is the position vector over here. So this is very important relationship for us. So now let's talk a little bit more about angular displacement vector. So first of all, we must realize the first point, that the direction of angular displacement vector d theta will be obeying. right hand screw rule. Okay, the meaning of this thing is, okay, so curl is anti-clockwise. So in that case, the direction of thumb would be outward. So the direction of vector would be like this. So if angular displacement is anti-clockwise, so its direction would be outward, and vice versa also. If it is clockwise over here, the sense of rotation is clockwise, then it would be inward. Okay, so that is how we choose the direction of angular displacement vector. And the second thing to notice over here is only infinitesimal angular displacements can be treated as vectors, and finite angular displacements are not treated as vectors. So let me justify this results with you first of all. The very first thing we must realize over here, the relationship which we have written over here, dr is equal to d theta cross r. But if we measure the finite displacement delta r, this will not be equal to delta theta cross r. We must realize, because in this triangle ABC, let's redraw this triangle over here. Let's say this triangle we have again drawn. This is A, this is B, and this is a C over here. And let's say this is this time finite, let's say delta theta, and this is basically over here R, and this is R as well. So in this case, delta R, which is this length AB over here, so delta R will be simply uh, 2R sine delta theta by 2, or you can say capital R can also be written as 2R sine phi into sine delta theta by 2. So clearly we can see, unless delta theta is very very small or tending to 0, we cannot have a relationship like this. So this equation is definitely delta r is not equal to delta theta cross r. So that is one of the thing. And another way of justification is, let's say, so if for a finite displacement, for a finite angular displacement, it does not commute. Means if a physical quantity is a vector, we can say, like for example, a plus b must be equal to b plus a. And if this law is not obeyed, that cannot be a vector. So let's look at an illustration, okay, proving this. That would be self-justified illustration. I have chosen the diagram already for you. So now look in this diagram. Let's say here we are having a cube, and these are x, y, and z axis, and this cube has several names on its face. Let's say this is 1, this is 2, and this is 3. Now imagine we rotate this cube about x-axis, okay, or so angular displacement, let's say, is theta x, and theta, we are rotating this cube by 90 degree. So what will be the orientation look like? So here, from this to this, if we are rotating by theta x along x-axis, okay, this face, this face over here will go up. So this will come over here, okay, this 2, and this 1 will be as it is, and the lower face will come to the right over here. So this is after displacing by theta x along x-axis by 90 degree. And now you see, if we after that, if we displace it, the angular displacement is theta y is equal to 90 degree along y-axis from this to this face, upper face will come in the front. So this face would be this over here. So first of all, the displacement in this case, the angular displacement, we can write it as theta x I cap plus theta y j cap. And now let's invert the sequence. This time here, we are starting from the same initial orientation, but this time only. First, we will be rotating by 90 degree about y-axis. So theta y is the angular displacement. So from this orientation, after rotating by 90 degree, it will become 1. So upper face will come in front and the left right face will remain at right. So this would be the orientation. And then after that, let's have the rotation about x-axis by 90 degree. Then you can say that lower face, the right face over here will come on the top over here. So this will become 2. So although we have so this displacement we can say is theta y j cap plus theta x I cap. Only the sequence of the rotation has been changed. But as you see, we have started from the same initial orientation, but the final orientation here and the final orientation over here are not same, as you can see. So we can clearly say that theta x I cap plus theta y j cap is not equal to theta y j cap plus theta x I cap over here. So that means the angular displacement vector does not commute, means a plus b does not gives b plus a. Okay, so that is why we cannot treat finite angular displacement as vectors, but we can definitely treat small angular displacement, infinitesimally small angular displacements, as vectors over here. So having discussed that, let's get on to the another concept. So since we have defined angular displacements, now let's talk about angular velocity, and then we will be talking about its relation with linear velocity as well. So angular velocity omega is defined as rate of change of angular position, or you can simply say angular displacement per unit time. So omega is defined as d theta by dt simply. Okay, and now for the linear relationship with the relationship with the linear velocity, we can say that see, the previously we derived this relationship like dr is equal to d theta cross r. We will be using that relationship to establish another relation of omega and v. So now, according to this definition, d theta can be very well written as omega times dt, and that cross with r. So dr is equal to this. So now you can say that rearranging this equation, we will be getting dr by dt is equal to omega cross r. So this is the relationship over here, omega cross r. Or this you can say v is equal to omega cross r. Okay, and now about its magnitude. So V will be equal to omega r sine theta. Okay, and r sine theta would be nothing but capital R over here. Like in the very beginning, we looked at the triangle, or let's say it was moving along a circular path. So that triangle, let's draw over here. So if the point is moving along the circular path, okay, so this was d theta. So this was direction of angular velocity. Okay. And this was the direction of dr. So v would also be along omega cross r. V is basically omega cross r. So velocity here is along the tangential direction. So that is the relationship between angular velocity and linear velocity. Okay. Similarly, we can have a relationship between angular acceleration and linear acceleration as well in case of fixed axis rotation. Now you see, how is alpha defined? The angular acceleration alpha is defined as a rate of change of angular velocity d omega by dt. So now we are interested in finding out the relationship between alpha and a. Okay, so here a, since is defined as a, is basically dv by dt, and just now we have established a relationship for v. V is nothing but omega cross r. So this we can write it as d omega by dt cross r plus omega cross dr by dt. So this gives us d omega by dt. We have already defined it as alpha, so that will become alpha cross r, and this omega and dr by dt is nothing but v. And rewriting this equation, what we can say, alpha cross r plus omega, and v basically was nothing but omega cross r, we already established. Okay. And now let's look at this omega cross omega cross omega cross r vector. Okay, so let's have this circular path. Okay, so this vector would be r vector over here. So omega cross r, that was the velocity vector. Okay, that would be in this direction. That was omega cross r. And omega vector is in outward direction. So omega cross r. So omega cross r would be a vector pointing towards the axis of rotation over here. So in other words, we can write it as this will simply become alpha cross r, and this will simply become, you can say, rather negative sign here we will be using. So that will become omega square r vector. So this here is basically, you can say, at, or you can say that is tangential acceleration, and this term over here is directed towards the axis. So this term is AA, or that would be known as accipital acceleration. Please try to understand the difference between the centripetal and accipital. Centripetal is towards the center, and accipital here is towards the axis. So wherever this point we are taking, if we are trying to find out this component of acceleration, this will not be toward the center, but it would be towards the axis. Let's say, for example, this is the rigid body. Okay, so if it is undergoing fixed axis rotation, this will have two components of acceleration. One would be accipital, and the another would be, you can say, tangential over here. So please try to understand about these two components of acceleration whenever we are looking at that. So we have derived these relationships, and these will be further useful whenever we are looking into the kinematics of rigid body motion. Okay, so So here we have completed the kinematics of a rigid body motion or rigid body rotation over here. So now let's discuss about constraint of rigid body. So whenever a rigid body moves, okay, the motion can be translational as well as purely rotational, or it can be combined translational and rotational motion also. So in all those situations, we must be able to write the velocity constraint equation. So velocity constraint equation simply means that we must be able to relate the velocities between any 2 points on the rigid body. Let's say, for example, uh, let's take this. So say we have some rigid body and it is moving, and we have chosen some 2 points A and B on that rigid body, and let's say this is the line joining AB, and the distance between point A and B is L. Okay, and point A is moving with some velocity VA, that is making an angle theta A with the line of separation. And let's say there is another point which is moving with velocity VB, okay, and it is making an angle of theta b with the line of separation over here. So the velocity constraint is about relating VA and VB over here. So will we be able to do that? Yes, definitely. So the thing is, this is a rigid body. So throughout this motion, no matter how this rigid body moves, okay, so here point A will be moving, point B will be moving, but throughout this motion, the distance or the separation between point A and B will not change. It is going to remain as L. So this thing is basically a part of rigid body constraint. This is a rigid body and its shape and size will not change with respect to time. So the distance between A and B is not going to change. So if the distance between A and B is not going to change, so that means the relative velocity of point A and point B along the line of separation is going to be 0. So for that, let's resolve the velocities of point A and point B in two mutually perpendicular components. So let's say this would be VA cos theta A, and this would be VA sin theta A, and this component here would be VB cos theta B, and this component here would be VB sin theta B. So we must understand, so the component of velocities along the line of separation, this component and this component, so relative velocity along this line is going to be equal to 0. That simply means that velocity of point B with respect to point A along the line of separation, that would be simply VB cos theta B minus VA cos theta A, that is going to be 0. Since the line along the line of separation, the separation is not changing. Okay, so that simply gives us VB cos theta B is equal to VA cos theta A. So this is the velocity constraint relationship. And not only this, we can find out the since it has point, every point has, here we can see in this diagram, has a tangential component of velocity also. So we can find out the angular velocity of this rigid body with respect to any point on the rigid body. Let's say, for example, uh, let's redraw this diagram over here. So let's say, redrawing this diagram, let's say this was rigid body and this is point A and this is point B. Okay, so if we observe the motion of point B with respect to A, So this distance is going to be L, and B is not separating with A uh, with respect to time. So the velocity of point B with respect to A along this line is going to be 0, but it is going to have a tangential component of velocity. So that would be, you can say, like VB sine theta B minus VA sine theta A, that we can safely say. So since point B is moving tangentially with respect to A, that we can say that it will be having some angular velocity omega. So omega B with respect to A we can very well calculate. So omega B with respect to A we can calculate, that will be simply tangential velocity upon L. So that would be VB sine theta B minus VA sine theta A divided by L. Not only this, similarly we can calculate the angular velocity of A with respect to B. So let's say this is point B and let's say this is point A. So this time what we can do here, and this angular velocity you can say is in clockwise sense. Okay, so if we imagine B to be at rest, the velocity of point A with respect to B is simply going to be in this direction. We can say that is going to be V VA sine theta A minus VB sine theta B. Okay, and this distance is L. So the angular velocity would be in this direction. So omega here, that is in anti-clockwise direction, omega A with respect to B can be written as VA sine theta A minus VB sine theta B divided by L. So this angular velocity we have written in opposite direction. Okay, so basically they have opposite signs. So basically what we can say is omega BA is nothing but equal to omega AB. So from this we can withdraw the conclusion that the angular velocity of rigid body with respect to any point on a rigid body will be same. That means uh, with respect to any point on the rigid body, if you are finding out the angular velocity of the rigid body, it is going to remain same. So it is not necessary to mention that about which point on the rigid body we are finding the angular velocity. So later on we can simply use the word that the angular velocity of this rigid body is this much, and we do not need to mention the axis about which we are finding out the angular velocity, because about any axis, okay, passing through the rigid body or in the frame of rigid body, it is going to be same. So that we can simply say. So what we have learned in this discussion, that how we can relate the velocities of any 2 points on the rigid body. Okay, and the another thing, we are able to find out the angular velocity of the rigid body as well. Okay, so looking at that, we have learned how to write the velocity constraint equation. Next thing, let's try to solve a few problems here. So this is a very simple problems I have chosen for you people. So here in this diagram you can see that there is a wall and there is a floor. Okay, and a rod AB of length L is lying as shown in figure. And point A, this point A is moving with velocity VA. So what we are required to find is, first of all, we are required to find the speed of B at this instant. And the another thing, we are required to find out the angular velocity of the rod at this instant. So the velocity of one point we know, and velocity of another point we want to find out, and that we are going to do using the velocity constraint. So velocity of point B, it is quite clear that point B is constrained to move only in the vertical direction. So velocity of point B, we can say very safely that would be in vertically downward direction. And now, as we learned, we will be resolving the velocities of point A and point B in two mutually perpendicular directions. So this angle here is theta. So this is going to be VA cos theta, and this is going to be VA sin theta. And similarly, when we will be resolving VB, so these will be two mutually perpendicular components. So if this angle is theta, this is 90 minus theta. So this angle would be theta over here. So this would be VB cos theta, and this would be VB sin theta over here. And using rigid body constraint, what we can say that the velocity of point A as well as point B along the line of separation, these two components are going to be equal. So that gives us VA cos theta is equal to VB sin theta. So VB simply we get as VA upon tan theta. So that is our first answer to the first part of the question. And answer to the second part of the question is easy as well. So answer to the second part of question, let's say we are trying to find out the angular velocity of the rod with respect to point A. So with respect to point A, the tangential velocity of point B would be nothing but VB cos theta plus VA sin theta. Okay, and that divided by um, the separation between them, that would be L, and that would be in um, anti-clockwise direction over here. So that will be omega over here. So very quickly now let's move on to one another interesting problem, and we will be solving that problem using the velocity constraint. So now we are having, in this diagram, as you can see, we are having a rod AB, okay, which is lying as shown in the figure. Point A has a speed VA, this point has a speed VA as shown, and what we are required to find again, the speed of this point B and the angular velocity of the rod as well. The geometry of this question, you can see that this would be a right angle triangle, you can see. And let's say this point is O, so OC is H and OA is H as well. That gives us that this angle is going to be equal to 45 degree. So now let's begin to write the constraint equation. Okay, so this rod is supported over this point C on the wall here. So this point C on the rod is constrained to move only along the rod. So this is the direction of the velocity of point C. So this is VC. Okay, and similarly we can resolve the velocity of point A along two mutually perpendicular direction. So that is going to be VA cos 45 degrees. So that is going to be VA by root 2, and this is going to be VA by root 2 as well. So writing the velocity constraint equation between A and C, what you can say, like VC simply can be written as VA by root 2. Okay. And the angular velocity of this rigid body we can find out with respect to point C over here. So with respect to point C, omega you can find out. With respect to point C, point A is moving tangentially with velocity VA by root 2, and the separation between them. So if this is H, this is H, so the separation between point C and point A is nothing but root 2h over here. So omega we have found out to be equal to Va by 2h. So this is the answer for the first part. Now we are required to find out the velocity of point B. Okay, so point B, we must clearly understand, like it will have a component of velocity along the rod, and it will have a component of velocity tangential to this rod or perpendicular to this rod. So this component is going to be same as velocity of point C, or you can say velocity of point A along the rod. So finding out this component is really easy. So this component is simply Va by root 2. What about this point B over here? So since we have already found out the angular velocity, so the angular velocity about point C of this rod, we have found out that would be in clockwise direction. So omega we have already found out. So velocity of point B, we can say that would be simply omega times this CB distance, and CB distance would be the length of this whole rod is L, and the length of this part AC is nothing but root 2h. So omega minus omega into L times L minus root 2h, you can say. And let's now substitute the values. So omega would be nothing but Va by 2h, and that would be L minus root 2h. So this is what you can say VB tangential. This is VB tangential. And if we want to find out the speed of point B, VB can be written as the axial component, that would be Va by root 2 whole square plus Va by 2h into L minus root 2a, and the square of this term as well. So this would be velocity of point B over here. So now let's try to learn about the acceleration constraint equation. The acceleration constraint equation, we need to look at it very closely, because this is one of the confusing things, and most of the students commit mistake while dealing with the acceleration constraint. So let's say we have a rigid body, okay, and we have selected 2 points A and point B on that rigid body, and let's say um, this is the line joining point A and B, and their instantaneous separation is L. So acceleration of point A, let's say, is AA, and the acceleration of point B is, let's say, some AB over here. So AA is making an angle theta A with this, and AB is making an angle theta B with this. Okay. So can we write down the acceleration constraint equation? It would not be as simple as that of velocity, because let's see, let's try to look at the motion of B with respect to A. So in the frame of reference of point A, this diagram will look something like this. Okay. So before doing that, let's resolve these components along mutually perpendicular directions. So this is going to be AA cos theta A, and this is going to be AA sin theta A, and this is going to be AB cos theta B, and this is going to be AB sin theta B. So if we analyze the motion of point B with respect to point A over here, so we can imagine point A to be instantaneously at rest. Okay, so here what we can imagine, that point B is accelerated. Point B will be having two components of acceleration with respect to A. One would be centripetal component, and the another would be the tangential component, AC and AT over here. That is, we can say, because point B is undergoing a circular motion about point A. So it is going to have a centripetal component and a tangential component. And just by looking into this diagram, AT or AC, simply we can say AC would be uh, um, AA cos theta A minus AB cos theta B over here, and AT simply is going to be equal to um, AA sin theta A plus or sorry, that would be simply AB sin theta B minus AA sin theta A. Simply, we are finding out the acceleration of point B with respect to point A in centripetal as well as tangential direction using the concept of vector subtraction. Now, in uniform circular or in circular motion, just now fixed axis rotation, we have learned that the centripetal or accipital acceleration was simply equal to, here it you can say that would be omega square L, and that would be omega square L, and this term here, tangential acceleration, would be nothing but L alpha over here. So using the equation number 1 and equation number 2, using equation number 1 knowing the acceleration of A, we will be able to find out acceleration of B as well when we will be knowing the angular velocity of the rigid body. Okay, and using equation number 2, we must be able to find out the angular acceleration of the rigid body over here. So this is going to be these two relationship is going to be useful in for the acceleration constraint equation, as well as it will be useful to find out the angular acceleration of the rigid body over here. And in ground frame of reference, we can say, let's say this is point A and this is point B. Okay, and we are able to find out the acceleration, centripetal acceleration and the tangential acceleration with respect to point A. But point A, let's say, also is moving with some acceleration AA. So in order to find out the acceleration of point B, okay, we need to vectorially add the acceleration of point A on this. So what we can say that in ground frame, now you can see in ground frame, okay, the acceleration of point B will be the vector sum of AC plus AT plus AA. So these discussion are going to be very, very useful when we enter into the problems of combined translational and rotational motion. So please do remember this. Okay, so now let's take one very simple question over here, where you will be using the acceleration constraint equation. So here in this question, you see a rod AB of length L is lying as shown in the figure. At the instant shown, point A has speed VA. This point A has speed VA as an acceleration AA, and we have to find out the acceleration of point B, and we have to find out the angular acceleration of rod as well. So let's draw this figure, okay, again, and this time we will be looking for acceleration of point B with respect to point A. So the acceleration of point B would be in this direction, let's say that is AB over here. Okay, so with respect to point A, so since the acceleration of point A is in rightward direction, so we need to subtract the acceleration of A in the acceleration of B in order to get the acceleration of point B with respect to point A. This angle is theta. So here this angle is going to be theta and this angle is going to be theta as well. Okay. So now let's try to use the acceleration constraint equation. So the centripetal acceleration of this point B would be simply, there would be a component of AB along this direction. So that would be, I am writing the centripetal acceleration, a centripetal of point B. So that would be AB sine theta minus AA cos theta, and that would be equal to omega square L. Okay, and in the previous problem, we already found out the value of omega to be equal to VA by L sine theta. So we can use that in this question over here. So, and using the value of omega, we will be simply able to find out the value of AB, and this will turn out to be VA square divided by L sine square theta plus AA cos theta into 1 by sine theta. So using this acceleration constraint equation along the line of separation, we must be able to find out the acceleration of point B. Okay, and now we are required to find out the angular velocity. So angular acceleration. So angular acceleration alpha would be simply tangential acceleration. Alpha would be nothing but tangential acceleration divided by L. So tangential acceleration, we can simply say that would be AB cos theta plus AA sin theta divided by L. And since we have already found out the acceleration of point B, so AB we can substitute from, let's say, equation number 1, and after substituting that alpha we will be getting as 1 by L into AA sine theta plus VA square divided by L sine square theta plus AA cos theta, okay, into cot theta, you can say. So that will be the relationship for alpha. Okay, so it is so we have learned in this discussion how to use rigid body constraint to find out the acceleration as well as velocity of any given point, and we must be also able to find out the angular velocity and angular acceleration of the rigid body. Let me state again that whenever we are saying that we are finding out the angular velocity or angular acceleration of rigid body, we do not need to mention that about which axis we are finding it out, because those physical quantities, angular velocity and angular acceleration, will tend to be same, okay, about any axis passing through the rigid body. Okay, so here we learned about the rigid body constraint, and now the last thing we are going to discuss very quickly is about the moment of inertia. So we are left with very little time, so we will start the discussion and we will continue with that discussion of moment of inertia a little bit in the next lecture here. So moment of inertia. Okay, so how this concept of moment of inertia arises, let's look into one picture. So let's say we have some rigid body of mass m, and which is undergoing, let's say, purely rotational motion or fixed axis rotation, and this rigid body is rotating with angular velocity omega about this axis. So we wish to find out the kinetic energy of this rigid body. Okay, so to find out the kinetic energy of this rigid body, let's take a small element of mass dm, and this dm, since this body is moving with uh, angular velocity about this fixed axis, so this point dm would be moving with, let's say this is at distance r from here, so it will be moving with tangential velocity v is equal to r omega, we can say. So the kinetic energy of this element dk will be equal to uh, half times dm into v square, and v we can write it as r omega. So this will become half r square omega square into dm. So if the total kinetic energy we wish to find out, so we need to integrate this term, and this will become half, and there would be an integral sign, so that would be r square dm, and that multiplied with omega square. So if we wish to find out the kinetic energy of this rigid body, which is undergoing a fixed axis rotation, we need to find out this quantity, integral of r squared dm over the volume of this rigid body. So this is a very, very important physical parameter, and this is known as basically moment of inertia of this body. Okay, and always understand, like whenever we are defining the moment of inertia of a rigid body, we are defining it with a given axis of rotation. So here this is the moment of inertia about this axis. Unless we mention the axis about which we are finding out the moment of inertia, this term moment of inertia has no physical significance. Okay, so let's very quickly go through some important type of or regular continuous mass distribution and learn the formula for them. So first of all, let's say if this is an axis, and we have a point mass m situated at distance r from it, so the moment of inertia would be simply mr square. Now one thing I want to point out over here, so irrespective of where this point is, where this particle is, this particle can be here, here, or anywhere. Okay, as long as it is maintaining the distance r from the axis, its moment of inertia is going to be mr square. So moment of inertia is a physical quantity which depends upon the mass distribution uh, with respect to axis only. So with respect to axis, if the mass distribution is not changing, the moment of inertia of the rigid body or any type of the body will not change. So other formulas, let's say a ring, we have a ring, okay, of radius r and mass m. So its moment of inertia about this axis I is going to be mr square simply. And if it is a uniform disk, if it is a uniform disk, its moment of inertia about this axis is going to be equal to mr square by 2. Now I want to add one thing over here. So let's say if we are having a partial ring, let's say from here to here only, okay, this partial ring, okay, and it has some mass m as well, or here in this case we have some partial disk over here, only this part, and this has also mass m and radius r. So now in this figure you can see that only like whatever mass was distributed in this part, now it has got redistributed over this part only. So doing in this change, the distance of mass with respect to axis has not changed. So the moment of inertia of this partial ring will also be equal to mr square. So here in this case, the nature of mass distribution with respect to axis has not changed. So I here also of this the disk which has been cut, also that would be equal to half mr square. So notice that mass m is also the mass of the remaining disk as well, or whatever the mass of the remaining disk, that you can substitute it over here. Okay, so the moment of inertia of hollow cylinder will be same as the moment of inertia of ring, because same type of mass distribution we are having over here. So I would be mr square, and the moment of inertia of a solid cylinder would be same as moment of inertia of a disk, because of same type of mass distribution with respect to axis, and that would be equal to mr square by 2. We can have the formulas for um, uh, a rod. Okay, so let's say this is a rod of mass m and length l. So this is one of its principal axis. So moment of inertia about this would be nothing but ml square by 12 if we are having a rectangular lamina. Let's say this side is A and this side is B. So moment of inertia about this side would be 1 by 12 ma square, and the moment of inertia about this side would be 1 by 12 mb square, and the moment of inertia about an axis passing through this here would be I is equal to 1 by 12 m a square plus b square. Okay, and one another important result, okay, of a triangular lamina. Let's say we have a triangular lamina of mass m, and it's let's say we are trying to find out the moment of inertia about this axis, and let's say this is height h. So I would be nothing but 1 by 6 mh square. Apart from that, in order to find out the moment of inertia about some other axis, we use two other important theorems. One is known as parallel axis theorem, and it simply state like if we have a body and we have a center of mass here, and we wish to find out the moment of inertia about some axis. Okay, so what we can do, we can find out the moment of inertia of this body about an axis passing through the center of mass, and that axis should be parallel to the axis, to this axis. So this we will term it as ICOM. So in that case, I would be equal to ICOM plus mh square, where h is the perpendicular distance between these two parallel axes and m is the mass of the body. Okay, and the another important theorem is known as perpendicular axis theorem, and it simply states that, okay, if we have a two-dimensional body, let's say we are having it in xy plane, perpendicular axis theorem would be applicable only for two-dimensional body, and we know the moment of inertia of this body about x-axis, and we know the moment of inertia of this body about y-axis. So we must be able to tell the moment of inertia of this body about z-axis as well. And this is all about the perpendicular axis theorem. It simply says Iz would be equal to Ix plus Iy, where you must notice that the plane of the body is in xy plane and z axis is the perpendicular to the plane of the body. Okay, so this is perpendicular axis theorem. We are going to use, so most of the times we remember the formula for the moment of inertia about some principal axis. So using that result in combination with parallel axis theorem or perpendicular axis theorem, we must be able to tell the moment of inertia about some other given axis, and that information about moment of inertia is going to be very, very useful in the discussion of rotational motion. And here I am ending this class. We are left with some problem discussion related to moment of inertia. So we will continue with this in next lecture. Okay. So thank you.